Long bone fractures failing to heal due to overly rigid implants is a significant healthcare problem. But how can we design new devices that are flexible enough to promote healing, but strong enough to withstand the complex loading in the body? I'm Huxman, a Rice Graduate Fellow at Penn State, and I'm excited to share some of the technology I'm working on for my PhD research here in mechanical engineering, which is really investigating this research question. But first, I want to introduce our awesome research group and some of its people. I do research in the Mechanism Collective at Penn State, where we study compliant mechanisms. These are mechanisms that get their motion through elastic deflection, so think bending, twisting, or stretching of flexible members. These kinds of devices have many advantages, including reduced part count, decreased friction and wear, and the ability to store strain energy, making them desirable in a wide range of applications. Our PI is Dr. Jared Butler, Assistant Professor in Engineering Design, who has extensive experience with compliant mechanism design in many of these different areas. So we've got quite a range of projects going on across many disciplines, and what I'm working on is compliant mechanisms for use in the body as orthopedic implants. So if you know anyone who's broken one of the larger long bones in their body, there's a good chance they were treated surgically with a fracture fixation plate and screws. These are very common stainless steel or titanium implants which do a pretty good job of stabilizing fractures and bringing the bone fragments back together. However, what we're learning is that for many of these fractures, overly rigid fixation can actually inhibit bone healing. So to optimally stimulate new bone growth at the fracture site, you actually want a controlled amount of motion between fragments. So this is where I'm using compliant mechanisms to design bone plates that might look or feel similar to what's currently used, but are designed to allow controlled axial motion up to a certain point. We don't want to overstrain the fracture gap. And by using compliant mechanism design principles, we can modify the geometry of the flexible members to control the stiffness and the stresses present during loading. Since these proposed plates are single-piece mechanisms, we can reduce or eliminate friction, wear, and detailed assembly that other multi-component concepts involve, and we can potentially do this without a major cost increase due to their planar single-piece manufacturing. Now, this is an inherently multidisciplinary project, which is why I'm thrilled to have these great clinical collaborators who are helping advise on the project in different aspects ranging from biomechanics to surgical technique. It's really valuable to have input from experts on the clinical care side who actually work with patients and handle these kinds of devices. We have simulated biomechanical loading in a simple humeral shaft model using finite element analysis, and our results suggest that compliant plates can significantly increase both the magnitude and symmetry of motion across the fracture site. So this has the potential to increase the strength and rate of bone healing, but there's a lot of unknowns still. And we're working towards higher fidelity benchtop validation and also rapid analytical models that can predict what the plate is going to do and inform its iteration and redesign as we target different anatomies or different types of fractures. I'm very grateful for the fellowship support received from the Center for Biodevices here at Penn State, and I look forward to gaining momentum with this project and continuing to get to work with these great people every day.